Tenemos ahora la conferencia magistral del profesor Bhadeshia. El profesor Harry Bhadeshia es bachiller en Ciencias en la Politécnica de la Ciudad de Londres, es PhD en la Universidad de Cambridge. Él ha realizado importantes estudios sobre la teoría de transformaciones de fase de estado sólido y en particular en la predicción y verificación de desarrollo microestructural en aceros multicomponentes. Su trabajo representa una gran contribución para la comprensión de la transformación vainítica, desarrollando y usando la teoría termodinámica para mostrar que los diferentes modos de transformación tienen influencias medibles sobre la microestructura final. Dejo con ustedes la palabra para el profesor Bhadeshia.
Jose. First of all, thank you to the audience for actually coming to this session so close to lunch. I'm very grateful that I have someone to speak to. I'm going to talk about how to control the residual stresses in weld deposits, and I'll go into that in a bit more detail. But you will see a website link at the bottom, which contains a great deal more of information which you can just freely download. Now, we construct very large structures. For example, this oil rig, it has a height about 3 times greater than what you see under the ocean, and very, very thick steel in many of its components. And one of the problems with welding is that you make a joint, and as it cools, it's constrained by all this material around the weld. And that means that the thermal contraction leads to a development of a state of stress, which is basically the yield strength of the material. So even before you load the structure, there is actually a built-in stress inside the material, and that's what we call a residual stress. And there's work going on all over the world now to design welding alloys which will compensate for the thermal stresses and at the same time have properties which are acceptable for weld deposits. So for example, I know that Professor Liu from Colorado School of Mines has published a few papers on this subject as well. So let me explain the problem very briefly. You see a weld preparation there, a V joint, which has nothing in it. And welding, fusion welding in particular, you put liquid metal inside that gap. And while it's liquid, it can not support any shear stresses, so there's no problems about stresses building up. But once the material becomes solid and it starts to cool, it's going to pull against all the surroundings. That means thermal contraction stresses. And that's when the residual stresses get built into the structure by thermal contraction. So what we have to do is find a mechanism of cancelling out those thermal contraction stresses, thermal contraction strains. And how can we do that? Well, this is a simplified slide showing all the phase transformations, the major phase transformations that occur in steels. On the left-hand side, you've got what we call the reconstructive transformations, where there's a lot of diffusion. And when diffusion happens, that's almost like fluid flow, and therefore you don't get any transformation strains. That means a strain caused by transformation. On the other side over here, you have the displacive transformations. Now the meaning of displacive is that when we change the crystal structure from austenite to ferrite, it doesn't involve any breaking of bonds. Okay? Basically, the shape of the austenite unit cell is deformed into that of the ferrite unit cell without any breaking of bonds. And this includes Wiedmann-Staden ferrite, bainite, acicular ferrite, and martensitic transformations. They don't involve any long-range movement of the ion or the substitutional atoms. And just to illustrate that, this is a square pattern to start with. And you can see that without breaking any bonds, I can change the way in which the atoms are arranged, okay? Just by a physical deformation. What that means is that the external shape of the crystal will also change. So this is deformation being caused by a change in crystal structure. And the basic hypothesis is that we can use this deformation to cancel out the effects of thermal contraction. So this, of course, is a schematic illustration. In the next slide, I will show you the real deformation that happens when austenite transforms into bainite or martensite. So we start with a sample of austenite which is polished completely flat, and you'll see that the transformation to bainite produces upheavals of the surface which are very, very large. So here you are. You can see a movie where the temperature is dropping from something like 550 degrees centigrade downwards. And when the transformation happens, you get these massive deformations, like the formation of a mountain range. So the shear strains there are about a quarter, very, very large shear. And there's also a volume change of about 3%. So the idea is, if we can design a welding alloy which takes advantage of this deformation to cancel out thermal contraction strains, then we get zero residual stress. Now, where does this idea come from? Well, it comes from back in the 1970s when Olbrey and Jones did these very beautiful experiments, all right? So what we have is a tensile specimen. We heat it up to 1,000 degrees centigrade, and we constrain it so that the ends cannot move at all. Okay, so it's held tightly at 1,000 degrees centigrade. As it cools, thermal contraction happens, and you can see that the stress rises. This is a fully austenitic specimen. Okay, it's an austenitic stainless steel, and all we are getting is thermal contraction strains together with some plasticity, because the yield strength of the material is quite low at high temperatures, and you get a buildup of stress. So this is sometimes called the Sato test. So thermal contraction leads to an accumulation of stress in our constrained sample. Now, supposing that we take another steel which doesn't remain fully austenitic, but it begins to transform at a low temperature. So here in green, we have a steel which will transform into bainite, and while it is austenitic, it builds up a thermal contraction strain, but you can see that as soon as transformation happens, the stress decreases because the deformation due to transformation is cancelling the thermal contraction. And once the transformation is finished, then the stress begins to rise again. So you can see over here, the stress has begun to increase because the transformation is exhausted. So we've got to control the temperature at which transformation happens so that it is not completed by the time we reach room temperature. So this is the third experiment that Olbrey and Jones did, where instead of bainite, you're getting martensite, which is forming at a lower temperature, and therefore we've reduced the amount of residual stress at room temperature. Yeah, because the transformation has happened at a lower temperature and it gets exhausted at a lower temperature, so you don't build up contraction strains after the transformation is finished. So the aim is to get the minimum here, this point, such that we end up with zero thermal contraction strain at room temperature. Okay, so this is the basic hypothesis which came about in the 1970s. Now, they were studying some other phenomenon, not trying to design any welding alloys. But when we design any welding material, it doesn't just compensate for residual stress. It has to have a whole combination of other properties which are good for the joint. So, for example, everybody knows that, the Charpy toughness has to be acceptable, and the fatigue strength has to be acceptable, corrosion resistance and crack growth rates, everything. So it's not easy to design a welding alloy which will transform at a low temperature and yet have the whole combination of properties. If I asked any one of you or anyone in the world to tell me how to calculate any of these properties, you could not do it. Okay? You can measure these properties, but If I gave you a chemical composition, heat treatment, etc., you would not be able to calculate any of these properties. These are incredibly difficult properties to model. Okay, so there is absolutely no theory which will allow you to calculate the Charpy toughness, the fatigue strength, the corrosion resistance, the critical stress intensity, and even the simple tensile test. Nobody can calculate it in spite of all the dislocation theory, etc., etc. The problem is just too complicated. There are so many variables in the composition, so many variables in the heat treatment, and so much microstructural change. But I want to be able to design a welding alloy as much as possible by calculation, and then make it and reduce the time scale from idea to production. Okay, so how do I go about calculating such a complex problem which nobody in the world can do at the moment? Okay, we had a talk earlier in this conference about machine learning, and I'm going to just give you a very brief idea of what that means. So in the welding industry, we have a lot of empirical equations. You know, for example, the carbon equivalent, and so on, and they work pretty well, right? And we use empirical equations when we don't understand the problem sufficiently to be able to calculate, all right? Now, machine learning is like regression equations, all right? It is a completely empirical method of recognizing patterns in very complex data. But regression analysis is a subset of machine learning, which is not sufficiently complex to deal with problems like mechanical properties. So what do we do? Well, let me give you an example. This is one of my former students, a lady called Tracy Cool, who was working on designing welding materials for steam turbines. And you can see it's a very, very big object, and it is also a safety critical object. And if I had to make a welding material for this, these are the variables that you need to think about. Okay, so there are chemical composition components. Some of them are in parts per million, but still very important. So for example, boron is only in parts per million, but has a big effect on properties. Oxygen concentration, etc. Then there will be some sort of thermal treatment that you give. And of course, you can have different kinds of welding consumables. You can have a stick electrode, you can have a cord wire electrode, and many different welding processes, and then heat treatments to change the state of stress. So the number of variables is far too large to be able to have a rigorous theory. So what you do is you reduce the problem. You treat a chicken like a sphere. Okay? So you say there are only two important variables, x and y in this case. And you have a graph where you have a set of random points. Doesn't make sense, right? By simplifying the problem, you've actually destroyed the technology, right? So I'm going to show you what happens in this random set of points when I introduce two more variables which affect the properties. So I'll introduce the z-axis and time, and the picture will become absolutely clear. Yeah. You can see that by ignoring the z-axis and time, you've completely lost the meaning of those points. All right? So simplifying the problem does not get us to the right answers. Okay? We have to actually treat the problem at the level of complexity that is posed. Okay, how do we do this? Well, first of all, you need to abandon the linear equation. All right? We want to make our model as a function of all those variables as nonlinear as possible, like this. Here we have just 4 variables, okay? And you can see that I can make my mathematical function as complicated as I like simply by varying the coefficients, okay? So mathematically, it's quite possible to produce very complex functions to represent the data. And of course, we have huge quantities of data in the literature, huge quantities. Metallurgists have been doing experiments for a very long time. We need to extract those data, to examine those data, assess them, and produce a knowledge base with which we can fit a complex mathematical function. But then you have to be careful, all right? You have to be careful about uncertainties. Particularly careful because we are dealing with nonlinear functions. So here, for example, I have experimental data as blue points, all right? But you can see that I can fit 3 different curves to the same experimental data to the same level of fit. But in between those data, the functions are behaving quite differently. Yeah? When we extrapolate, they are not producing the same result. In the middle, you have a large difference between the 3 different models. And this is what we call modeling uncertainty. That means for the same set of data, you'll be able to find many different models which fit the data reasonably. So this kind of an error you don't have in your regression analysis because you're just fitting a single straight line to the data. Okay? So we need to have 2 kinds of error bars. One is when you repeat an experiment, you get a different answer because of noise. That means some uncontrolled variable. And this is a second kind of uncertainty which tells you that your mathematical models themselves are not very certain. And it's very important to have this because it gives you an idea of the danger of extrapolation, interpolation. And frankly speaking, if you are designing something new, then you will be in a region where there is no knowledge. All right? So you should expect to see a large uncertainty. So in machine learning, it isn't simply about fitting some function, but you need to treat the uncertainties very seriously. Okay, so the solution, so there's a long story about this, which you can see on my website, and there are videos explaining it all. But I'm going to summarize that machine learning actually has made major advances into the treatment of mechanical properties in steels in general and welding in particular. And we use nonlinear functions, very large number of variables, any number of variables. So for example, when we model a rolling mill, we have something like 200 variables. And a serious treatment of uncertainties, and we exploit all the data that exists in the literature. Okay? By doing that, we can make predictions, all right? So going back to the story of canceling residual stress, the idea is to use transformation strains to compensate for thermal contraction. And we need to generate those transformation strains at a low temperature. And that means that we should use martensite. Now, people in welding don't like martensite, right? Because martensite is associated with bad toughness. But if you remove carbon, then martensite is actually very tough. Okay? So for example, rocket motor casings are made from martensite with 0 carbon concentration, Maraging steels. Okay? So martensite is not bad if you remove the carbon. Keep the carbon to a minimum. So if you make a martensitic welding alloy, it will transform at a low temperature, and it will completely cancel out the thermal contraction strains. But we need to make sure that the toughness is fine. So we designed a number of welding alloys using our mathematical models, and we came up with this, which goes against what we normally think. According to this, if I have 0.5% manganese in my welding alloy, and I increase the nickel concentration, I will get better toughness. But if I have 1.5 weight% of manganese and I increase the nickel concentration, then the toughness will deteriorate. Every book will tell you that if I add nickel to steel, the toughness will improve. Okay? This is saying no, it will not if we have 1.5 manganese. It's only if the manganese concentration is small that nickel will improve the toughness. Now, given that this is an unusual result, we need to test it. So we made 3 alloys, welding alloys like this, and alloy C should have really good toughness, whereas A and B should not. And indeed, when we make the materials, you can see that the models have predicted correctly that to get better toughness by adding nickel, you have to have a low manganese concentration. And there is a physical reason for this, which came out from this investigation, which I don't have time to go into right now. Okay, so assume that we've got all the other properties that are required from weld metals correct, and we've got a low transformation temperature. Sorry, I do have an explanation. So what happens when you have high manganese and high nickel is that the plates of martensite join up together, okay, to form very coarse regions. And when you have a coarse region, that will have poor toughness. So in the middle, you see a very big block of martensite, and that's not good for toughness. Okay, and there's a mechanism for this. It's called Coalesced Martensite. Okay, we designed these alloys. The first one is a commercial material which transforms at a high temperature. Okay, you can see that it is not very heavily alloyed, and it transforms at about 450 degrees centigrade. And the other three are alloys that we designed, all with low carbon concentrations, but sufficient alloying element concentration to reduce the transformation temperature to about 200 degrees centigrade. And we did a more complicated Sato test, where we take a tensile specimen, we constrain it at a high temperature, allow it to cool, and monitor the strain. This is a synchrotron, where you have high energy X-rays going through your tensile specimen while you do the Sato test. So that means we can follow the amount of austenite and martensite that forms as a function of temperature during the tensile test. And here you can follow the phase fractions as transformation happens. The blue curve represents the martensite, and the red curve represents the ferrite, and this is the commercial electrode. Okay, these are the equivalent of Albury and Jones results, where you can see in the pink curves where the transformation temperature is high and it gets exhausted by the time you reach room temperature. You're left with a residual stress of about 400 megapascals, whereas with the low temperature transforming welding alloys, you've ended up with zero or compressive stresses. Okay? Bear in mind, this is just a tensile test. In a real weld, you will have a complicated stress system. But the principle of cancelling out residual stresses using a welding alloy which transforms at a low temperature is proven. Okay, these are neutron diffraction experiments done in Canada at the Chalk River facility, where we made welds, and then we are characterizing the distribution of stresses. The top picture comes from the commercial electrode, which transforms at a high temperature, and you can see that there's tensile stresses everywhere. Okay, tensile residual stresses everywhere. But with the other two, right in the middle, you can see a compressive stress of minus 600 megapascals. So you've left the material in that region in a state of compression instead of residual stress. And that's exactly what we wanted, is to get rid of tensile residual stresses. Of course, we are not just welding mild steel. We are also interested in welding stainless steels, and not austenitic stainless steels, welding alloys, because austenitic welding alloys do not transform. So we wanted to design a stainless steel welding consumable which would be martensitic. And there's a number of design principles. The first is, obviously, for it to be stainless, you need a chromium concentration which is greater than about 12%, so that you get a chromium oxide film on the surface which protects the substrate. And it's a chromium oxide film which regenerates itself. So if you scratch the material, it will form instantly again. We need to keep the carbon concentration as low as possible, because we don't want chromium carbides forming and sensitizing the material. We need a low martensite start temperature, but not too low so that we don't retain too much austenite. And we don't want to use carbon. At high temperature, it should be fully austenitic, and solidification should be with delta ferrite, otherwise there's a tendency for hot cracking. Okay, so these are the design criteria. And this is what we did. So whenever we do some calculations and think of an alloy, we first make a very small quantity, like 50 grams or 800 grams. We test the basic principles, and then we get the welding consumable manufactured, in this case by ESAB. And we do a comparison against an austenitic stainless steel. So here are these alloys, and they're transforming at a reasonably low temperature of around 200 degrees centigrade. And I've simplified the composition here, so you can see that the main constituents are basically chromium and nickel. Okay, we also have to worry about chemical segregation. Okay, you can see that when you etch, I don't know where George is, but he would be pleased with the color picture showing the etching, illustrating the segregation. So obviously, if you have chemical segregation, you'll get different kinds of transformation temperatures. So the design of the alloy is not simple. There are many, many variables to take into account. Anyway, we did it, and you can see that the toughness results are pretty good. Even at minus 20 degrees centigrade, you've got about 50 joules of toughness. And I'm going to show you the manifestation of residual stress in a different way. This is distortion. Okay, so on one side you see a plate which is almost flat after welding, but on the other side you see that it's changed into a V shape because you've deposited the weld. So distortion is a manifestation of the residual stress, and it's an ugly feature when you're making very large objects. Okay? And you can see that by using the low temperature transformation welding consumable, you reduce the distortion from 7 degrees in this experiment to less than 2 degrees. Okay? So basically, the welding alloy works in compensating for thermal contraction by transformation strains. Okay, so the principle now of designing a welding alloy which will cancel residual stress is well established, and we can even do multi-run welds. That means not a single bead, but several beads, by ensuring that the interpass temperature is such that the whole weld transforms at the same time. Okay? So everything remains austenitic until you've completed the welding process. And that has been demonstrated. We are now working on looking at overloads. That means that supposing you have a Caterpillar tractor, all right? It's not going to just undergo a steady load. Sometimes it will hit a rock and you'll get a big spike in the load, and that can alter the residual stress system. So we're working with TWI to examine specifically the effect of overloads on residual stresses. Now, of course, I didn't do all this work myself. There's an awful lot of people there who participated in various aspects of the problem. Many of them have now left and are changing the world for the better. And I would also thank this university and the conference organizers, because they gave me my first opportunity in my life to look at what the Incas did. Okay? So here, for example, was a picture taken just a few days ago at Machu Picchu. You can see the beautiful constructions they did. And I couldn't have done this. I wouldn't have gone there on my own. I'm not a good traveler. But there were a couple of people here who decided they would like to take me to Machu Picchu. And we really had a lot of fun. Similarly, of course, I need to thank the organizers of this meeting. You can see Francisco actually wrote to me that, look, in 2015 you couldn't come because you were busy. Can you come now? He remembered from 2015, and I was delighted to receive this email. And while we were walking on this campus, we saw this impeller. You know, it's absolutely amazing technology, you know, for generating hydroelectricity. And it has weld repair done on it, you know, because water causes a huge amount of damage to these objects. I think it was the perfect exhibit for this university, you know. It's working on welding, and it's working on a problem which is so important for Peru, hydroelectricity. Okay, so I'll finish there. I've got plenty of time for questions, and I'll be very happy to receive them.
Thank you, Profesor Bhadeshia. Ahora vamos a pasar a ver si hay algunas preguntas del público. Si alguien tiene alguna pregunta. ¿No?
So remember, I've come all the way from England with an 11.5-hour flight, so I expect some questions. Okay?
¿Sí? Si alguien tiene una pregunta, por favor levante la mano para que le puedan alcanzar el micro. ¿Sí?
Come on, Stephen, you must have a question. Yep.
Okay.
Right. Very nice people who took you to Machu Picchu, huh?
Yes, absolutely.
So you have these consumables that can end up in either neutral or even compressive stresses in the well deposit, right? Now, right next to the well deposit, there's nothing you can do because it's the base material, and that's usually in tension from the
equilibrium,
cycle,
yeah.
right? So you can fix the problem at the well bead, right? But you still have the other problem. Now,
Correct.
when you do experiments, you improve fatigue life.
Yeah.
What do you think happens that you see
Yeah,
the
yeah.
other part?
It's a very good question because, for a body in equilibrium, if you have a compressive stress, you'll have a tensile stress as well. What happens in fatigue testing, which is what we do with these things, is that you have a stress concentration exactly between the weld and the plate, at the junction, because you have a bead. And if it's a fillet weld, it will be at the toes. And it is the stress in that region which is important, and that is reduced actually by using the low temperature transforming alloy. So you do have a compressive stress in the middle and a tensile stress in the adjacent plate, but at the toe of the weld, it's actually reduced from what it would have been if we didn't use a low temperature transforming alloy. Yeah? And that's where fatigue usually initiates. Okay. Stephen.
Well, Professor, excellent lecture.
Thank you.
Like the photos. I don't know about the two guys that accompany you. I do have a few questions.
Yeah.
I'd like to ask about the future of these LTTW consumables. How do you see the future of it? And then after you finish, I'll follow up with other questions.
Okay, yeah. So these are now commercially available, all right, both for the stainless steel and for the mild steel. It depends on which application. So if you have, I believe, I don't have the evidence, I believe that if you have a very large overload, that homogenizes the stresses. So whatever you built in will tend to get homogenized, and then we may lose advantage, all right? But we are gathering the experimental evidence by doing fatigue testing with huge overloads occasionally at random intervals, okay? But for many applications, you don't have overloads. In certain structural beam applications, for example, you don't have overloads. And in those applications, it would definitely increase the fatigue life. And we ourselves have designed a hydrogen-resistant steel for going under the sea, ocean bed. And for that, we are using the low-temperature transforming alloy, because, hydrogen effects are made worse by residual stresses. So in that scenario, you know, the combination of low temperature testing and hydrogen traps inside the steel might work better.
Second question, actually, Patricio kind of alluded to it, is not all the structures are made by single pass weldment,
Yep.
so multiple pass weld. And then each subsequent layer, you know, heat treats the previous ones
Right.
and all that. So then it becomes only the top
Right.
cap passes that.
Yeah.
So what is your view on that?
So we have solved that, okay? So let's assume the martensite start temperature is 200 degrees centigrade. Then we maintain the interpass temperature to be above 200, so that it's when the whole thing is completed, the weld as a whole transforms rather than sequentially. We've written a paper on this, which shows clearly the effect of doing that.
Okay, so just by controlling the heat, preheating,
Correct.
interpass temperature.
Interpass temperature,
So for the entire weld to transform to martensite at the same time?
same time.
Okay. My last question to you, is there an optimum amount of the martensite that you need? Because some of the prior work that we have done, that we have been targeting, is that there is an optimal amount and also the time of reversal from the martensite to austenite to martensite, you know, that controls the amount of residual stress.
Right. That's a good point. We haven't looked at that. In these alloys that we designed, basically there's almost 100% martensite by the time you reach room temperature, but I'll have to study what, you have written something on this, right? Yeah. Okay.
¿Alguna otra pregunta?
Yep. Over there.
Please, somebody, if you can help me in English, I ask in Spanish. Puesto que el crecimiento o la transformación obedece a planos y direcciones preferenciales, ¿están buscando que el crecimiento de la fase madre a transformar tenga solidificación direccional?
Yep.
The question is, given that the transformation is related to the prior austenite according to some crystallographic planes and directions, so if you aim to have some sort of directional solidification to set the stage right, is that more or less, ¿lo dije más o menos bien? Okay. Yeah.
Yeah, so it's a very good question. So theoretically, we have the framework and we have done the calculations of anisotropic transformation strains, okay? But if you have polycrystalline austenite, which is not textured, then that also will become isotropic. So when we control the interpass temperature to be above ms, we get epitaxial growth through the multi-runs, okay? And then we pick up anisotropic strains rather than just a volume change type effect. Yeah. Maybe you can translate? It's okay. All right. Yeah.
I have a quick question. When you do multi-pass, right, and you wait for everything to cool down together, if you have a big weld, maybe it'll take a while to cool down, right?
Right.
Is there any risk you might end up doing some sort of austempering instead of
Yeah.
martensite?
Yeah. I mean, this has almost no carbon, so the tempering basically doesn't happen. Yeah.
¿Alguna otra pregunta?
So we still have 5 minutes, all right? So you have to participate. Okay. Okay, I think we've run out.
I think-
Oh,
This one. 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 This
now I would like to know something about the characterization. Which is the methods you use to characterize the percentage of the martensite? Barhausen maybe? I don't know.
Yeah. What we did was we studied these alloys in the X-ray synchrotron. So we have a dilatometer fitted to the synchrotron so that we can follow the transformation as it happens, and the fraction comes out from the diffraction data. Yeah. Okay. Okay.
Okay. We would like to thank Professor Bhadeshia. Oh, they have one more question.
Oh, yeah, sure.
You know, I'm going back to the multi-pass well, and I kind of agree with Patricio, is the fact that, you know, the possibility of doing the, you know, austempering. Okay, you say, well, you don't have, you know, no carbon whatsoever, right? The questions that I have is, do you still, to go from the 200 or 250 degrees C, do you cool it immediately, or do you cool it, you know, slowly? What would the cooling rate have, you know, what impact would it have if you go like a quench or doing just a continuous cooling?
Just continuous cooling, because because the quenching won't be practical in real scenarios.
Right.
Yeah.
Okay. Sure.
¿Alguna última pregunta? ¿Tenemos tiempo para una más? ¿No? Entonces,
Okay.
we would
Thank
like
you
to
very
thank
much.
Agradecemos al
Thank you.
profesor Bhadeshia. Un fuerte aplauso.